Every challenge question, chapter 3 of book 2. This chapter is about, it's the series chapter called. So nth term of this is this, u3 is this, u7 is this. So just put u3 into here to get log 16, because that's what u3 is, equals log a plus 3 minus 1 log b. And likewise, log 256, if you use n is 7, replace that with the 7, you get this. Tidy those both up, you get this. And then, of course, we can take away a few things here. So I think I did this equation minus this one to get this. Log of 256 minus log of 16. You can type in a calculator if you want to, or you can use log laws, or you can really do whatever you want. This is 16. Of course, this 4 can jump up to here. Log of 16 equals log of b to the 4. 2 to the 4 is 16, so therefore b is 2, I believe. And I guess b could be minus 2. No, it couldn't, because log of minus 2 doesn't exist, so b has to be positive 2. Good spot. And find a, of course, just put it back in here. This is log 4, take it away from both sides, and divide, I guess, as well. And you get a is 4, and you have your two answers. Next one is very similar looking, right? Like the questions look basically identical. This is an arithmetic sequence. So, okay, the first term is when n is 1, so that's log 9 plus 0 log 3. Second term is n is 2, so that's log 9 plus 1 log 3. And we can see here that this is an arithmetic series with the first term log 9 and second term, and difference log 3, because that's what you're adding every time. This a doesn't refer to this a, I'm just being deliberately confusing. Some of the first n terms is given by this formula, so we're trying to find some of the first n terms. But we know a is this, so we can put that in. We know d is this, so we put that in. And yeah, then we try and sort this out. So, I mean, this 9 is 3 squared, right? And then we can put this 2 over here. This n minus 1 can go over here, and we end up with all this. In fact, actually, I'll put this 2 up there, I think. That's nice. Anyway, two logs adding together can multiply. So this will become 3 to the 4 times 3 to the n minus 1. And of course, when you times bases, you add powers to make this. That's, of course, just 3n plus 3. Then I've split this up, because what I'm going to do is I'm going to put this n up here, following power law, but leave the half behind. And we end up with exactly what we want to get, with a being a half from here. And yeah, that's good. Sum to infinity of this, so sum to infinity is a over 1 minus r. So that's 7 according to this. The second series is formed by squaring every term. So the first sequence or series goes a, ar squared, and so on. Because it starts at a and then you times by r every time. If you square every term, you're going to get a squared r squared r to the 4, and so on. Now this is just a geometric series because you times by r squared to get from one to the next. And the first term is just a squared. So that's cool. So that means it's geometric. The sum to infinity of the second series is 35. So the first term is a squared. So that means, and the ratio is r squared, so that means a squared over 1 minus r squared is 35. Going to be fancy here. This here can be written as a over 1 minus r times a over 1 plus r, because of the difference of two squares here. But this thing here is just 7, according to this. So that's there. Divide both sides by 7, we get this. And now focus on this thing here and this thing here. If we cross multiply that over there, we get a equals 7 minus 7r. And this one, a equals 5 plus 5r. Take these two things away. And, or in fact, is it this one, take away this one? Yeah, it is. Anyway, and you get r as a sixth. And that's all we had to do. Next one. So given this equals this, show this. So here, this looks like, well, I think what I did here, yeah, the sum of the first 10 terms. This is essentially just saying sum the first 10 terms of this. So the sum of the first 10 terms is this. So all I did was I put that into there. So I said, well, if r is 1, then this is just a. And if r is 2, this is a plus d. So this is similar to the previous question, where the first term is just a and the difference is just d. So I can just use these letters in this formula here, going up to 10. I'll simplify that a little bit, where n is 10, so this gets replaced with a 10 as well. Simplify that a bit, you get this. And then do the same with the right-hand side, except the right-hand side you need to go from 1 to 14, and then from 1 to 10, and take away, just so you're left with 11 to 14. So this is just the same thing now, just this formula, but with n is 14 and n is 10, and this take away this. Simplify that up a little bit. Eventually you get something that looks a bit like that. And now, of course, apparently those two things are equal, so we set this equals that. And take away 4a, take away 45d, and you end up with what they wanted you to get, which was cool. I think this is hopefully the last one. I'm not really sure, though. We've got a recurrence relation here that looks like this. Oh, I do remember this question. This was great. Anyway, ua is 1 and u2 is b. So that means u3 is 1 plus b over a. just following this procedure here. U3 is 1 plus U2 over U1, and we have this. Which means U4 is 1 plus U3, which is this, over U2, which is that. I'm going to try and simplify that up a little bit, because this can be written as A over A. So this is A plus 1 plus B over A, and then this all over A can just go over underneath there, and I think I'll end up with that. Which means that U5, and this is a complete mess, but let's just keep going with it. U5 is 1 plus U4, which is this, over U3, which is that. Okay, so this is AB over AB, so let's put those together, and then let's shift this AB down to here, and maybe this A all the way up to the top, and we get this. Hopefully, does some stuff factorize? Oh yeah, nice spot. That's a good spot there. This is AB plus A plus B plus 1. And now cancel those two things there. And you end up with just, and cancel the A's, of course, as well. And you just end up with this over that. So that's U5. So U6, therefore, is 1 plus that over that. This is B over B, so this becomes B plus A over 1 over B over this. But of course, B plus 1 plus A is the same as that. So I think that cancels with that. And I think we're just left with, and then of course, so that cancels with that. This B goes underneath, this AB goes on top. AB over B is just A. Yeah, so be comfortable with your fraction rules, because it does help here. Anyway, we finally got back to U1. But now we just need to show the next one is also B, because otherwise it's not truly periodic. So we'll do 1 plus A, that's the previous term, over the previous term, which is this. Of course, that cancels with that. 1 over B is just B. And this definitely is periodic. And the first term is equal to the 6th term, so it's period 5 or order 5, whatever you call that. Okay, in the case A equals 2 and B equals 9, find the sum of the first 100 terms. So if A equals 2, the first term is 2, the second term is 9, the third term is 1 plus 9 over 2, which is 5. The fourth term is 2 plus 1 plus 9, which is 12, over 2 times 9, which is 18, so I think that's 2/3. We're getting that right? Perfect. And the fifth term from here is 2 plus 1, which is 3 over 9, is 1/3. And then we get back to the first two terms. So I think that's the sequence. Good, except when we're adding the first 100 terms, we can just add, because this pattern, these 5 terms just repeat over and over again, we can just add the first 5 terms 20 times. And I think that will do it. So it's just 20 lots of all these things added together. This is obviously 1, and then you add the others, and then you times it by 20, and you get your answer. Is that the whole chapter done? No, it's not. There's another question. Oh my gosh. Anyway, maybe there's another one after this. I've really forgotten. Another recurrence-like relation to do. This is definitely the longest one we've done so far, I think. Prove this sequence of the form. This satisfies the thing. So okay, we'll just shove in un plus 1. So replace those with plus 1s, and then you could bring, this is essentially 3 to the n times 3 to the 1. So just put the 3 at the front and do this, and put this 2 at the front and do that. Un plus 2, the same thing, except this is a 3 to the n times 3 squared. 3 squared is 9, put a 9 at the front, and here put a 4 at the front. And then literally just put this thing in here equals 5 lots of this thing minus 6 lots of this thing, and check it works. Or if you're an idiot like me, start at the left-hand side and work your way towards the right-hand side, which is absolutely not how you should do this, but it is fancy. So okay, what we're going to do is we're going to say 9 is 15 minus 6, because we went to primary school, and we know that. And 4 is 10 minus 6. So that's really fancy. But then we're going to group it a little bit by the 15 and the 10 we're going to put first, followed by the 6 and the 6. And the reason I'm doing that is because I think I can factorize out 5 from this to leave behind 3 of the p's and 2 of the q's. And I can factorize out 6 from that to leave 1 of each. And I think this thing here is literally just un plus 1 by definition. And this thing here is un. And so therefore equals right-hand side, and we're done proving that. Given u1 is 5 and u2 is 12, so okay, well we can just put in 1 into here and 12 into here, and we'll do some solving. So if you put in u2 is 12, you get, what have I even done here? So 2, yeah, so 3 squared is 9, and then 2 squared is 4, and then put 12 over there, fine. Do double this one, I guess, to get 10, 6p, 4q, and then take away to get 3p equals 2, and then p is 2/3. And okay, and then we can find q, which is, well, that times 3 is 2, so that's 3, so that's 3 over 2. Good. So therefore UN is just replace the P and the Q with what you found, and you'll have your answer. Hence determine the number of digits. Now this question really pissed me off, because what I did was I put in 100, and then I was like, oh yeah, look at these 3s and 2s. This will work quite well. So divide that by 3 and you've already got 99 3s, and divide that by 2, you got 99 of those. And then I was like, oh, actually, but what if I took another one out of here, like another 3 out, because 2 times 3 is 6. And another one makes 6 there, and then I can factorize the 6 out. And then I ran out of ideas, and it turns out this is the first one of all the challenge questions I've done where I had to look at the mark scheme. It turns out you're just supposed to type that into a calculator, read this number, add 1 onto it, and say there are 48 digits. And that really annoyed me. That what is the point? Come on, guys, just write a question that is better than that. You know, not that hard.